Hello everyone, this is Priyanka from Edureka, and today we are gonna understand how game playing is implemented in artificial intelligence using alpha-beta pruning. So let's quickly have a look at our today's agenda. So we are gonna cover alpha-beta pruning, the working of it with an example, and also we will see a hands-on implementation of one game in Python, followed by the significance, advantages, disadvantages of alpha-beta pruning. But before we get started, make sure you subscribe to Edureka's YouTube channel and hit the bell icon to never miss an update. Also, if you're looking for an online training certification, do check out the link given in the description. So now let's understand what exactly is alpha-beta pruning. So alpha-beta pruning, it's a search algorithm and it is used in decision-making or game theory in artificial intelligence. Also, it is an advanced version of minimax algorithm, or you can say it is an optimization algorithm which improves the performance of minimax algorithm. And also it is used in games like tic-tac-toe, chess, and checkers. And this basic algorithm is the brains behind finding various moves and the best move for the players. So you must be wondering how this algorithm helps in searching the best move or finding the space searches. Well, for this, we will have to understand the working of alpha-beta pruning in artificial intelligence. So let's understand the working of it. So this is our game tree with different scores at the end of the tree, and this is the leaf node, that is the terminal, and we see here different nodes. Now you must be wondering what is this alpha and beta. So these alpha and beta, these are the players, and alpha will try to maximize the score and beta will try to minimize the score. Okay, and there's one condition of the rule that alpha should be greater than beta because you want to maximize the score. Very simple. And there's one more thing that needs to be noticed here is that, or kept in mind, that max player will move first, followed by the min player, and then max, and then min. And depending on the length of this tree, their chance will alternate, right? Since we find terminal here, so it will end here, right? But it will go on until the depth of the tree. And this alpha-beta pruning actually makes use of depth-first search algorithm. So in depth-first search, we just traverse from this node to this node until we reach the leaf or the terminal of the tree. So that is what we will be using here, the depth-first search, to find the best move, or our goal would be to maximize the score of alpha and to find the best move that alpha could make so that it wins. Okay, so we want that alpha should win. So we will do everything so that its score just maximizes. And for this, we have to find various spaces. This is really very interesting. So let's just see, and how do we really find these search spaces, and what role does alpha and beta have in this alpha-beta pruning. So now, since this is a depth-first search algorithm, so what I will do is we will start from here till the depth of the node from each node, and we find here that this is 4. Okay, so immediately what happens is that this goes here and says that, okay, beta update the value as 4. Here we see that this is a min node, and in min node, the value would be less than equals to 4. That means there is still a chance that I can get the minimum score, which could be less than 4, which would be good because I have to minimize the score. So what it does is that it says, okay, I will just traverse another node. So it goes and see the fifth, this node that is having 5. The score is 5 here. So it sees that, okay, 5 is not less than 4. So it says that I'll fix the value of this node as 4. So this min value is now fixed as 4. So what happens is just goes up, checks that, okay, this is alpha. That means it has to maximize the score. It says that, okay, you take your value as 4, right? And we have seen that alpha should be greater than equals to beta. So it always has to be greater than equals to 4. So I would have a possibility that my value could be greater than, I could get a good score, maybe greater than 4. So I will still explore for more chance. So what I do is, instead of updating, I will just check the another node here. Okay, for the time being it is 4. So it sees here it goes to beta, and then it goes to the last node, that is the leaf node, and it says it is 3. Okay, it goes above, it updates the value as 3. And since it is a minimum node, it says that, okay, the value could be less than equals to 3, but it will not be more than 3. But it says that, so it updates this value. Now it goes up and it says that, oh, this value is 4. That means anyways, this will maximize the score and will not choose 3. That means it will not choose this route, this path, because it already got a maximizing score. And here, if this would have been 5, then there would have been a chance to update this score. But it is not so. So what it will do, it will not traverse this path. because there's no benefit or use of going and seeing again this path. Okay, so what it will do, it will not go, it will prune this node and update the value of max as 4. Okay, so now after having fixed the value of this node, we will take this value above and we will see that, okay, beta, we got this value as 4, take this as 4. Now beta says that I have to minimize my score, so I will look for the values which will be less than equals to 4. Okay, so what happens here is that it will say that, okay, I got a possibility to explore other nodes also and spaces wherein I might get value which is 3, 2 or 1. So it goes down again and goes to the last node and sees that, oh, it is 7. Immediately comes back and says that, okay, beta is 7, but this is a minimizing node. That means it will be, values will be less than equals to 7, right? So it has to again check whether it might get, value 6 or 5. So it goes again and check this node and it says that it is 8. So it's anyways, this condition is fulfilled that 8 is greater than 7. So this node value becomes 7. Okay. Now this value is taken above to alpha and alpha says that, okay, this is 7. So, okay, I update this as 7, but this is a maximizing node. So I will want a value which is greater than equals to 7. So there's a possibility that I might get a better score than 7. So what it will do is, again, it will go above since it will check the above node and it says that, oh, so this is beta's chance and it will minimize the score. So anyways, it has an estimated value that it will be 4. So, and this is 7. So this would anyways not travel to this path, right? So even if I update my value as 7, this is not gonna choose me because it got its score as 4, which is minimum, right? Because it has to minimize the score and this has to maximize the score. But the above value will not choose it because it has already chosen a lower score, right? So what it will do, it will prune, it will not traverse all these nodes and they will get pruned, right? So the search space to go to these nodes, traverse and then update will be reduced by alpha beta pruning. Okay, so now we come to this node again, and since the value of minimum here node is fixed, that is 4, it will take the value above and says that, okay, alpha, we've got 4 here, so it says that, okay, the value will be 4. And since it is maximizing, so I can get a value which is greater than equals to 4, right? So we have to explore more possibilities or search spaces so that our score just maximizes. And we've got this right node here, the search to begin. So again, we will start our search. So for this, in the depth first search, we will first go to the left node. So we will start from here, okay? So now we'll go to the depth and we find here 2. And immediately when we find 2, we will update beta as 2. And since this is again a minimum node, the value would be less than equals to 2. So far, so good. Now again, if we might find 1 here, so let's just traverse 12. And it says that, oh, this is greater than 2. So we will update this as 2. Now this value, when it's fixed, we just take it above and say that alpha, it is 2. But this has to maximize the score. So the value would be greater than equals to 2. All right. Now, it has again got the possibility to explore the values. That means we can maximize our score. So it will go to the, again, the terminal node of this left child. It says that this is 1. So the score of the beta would become 1. And again, if it will traverse 13, it will say that, okay, anyways, this has to be less than equals to 1. So 13 cannot possibly come. So it will fix this node's value as 1. But when it sees that this is alpha, and this will maximize the score, that means it will not go to this path. So it will fix it and choose the value as 2. When its value is fixed, we will move above, and that is beta here. Again, this will try to minimize the score, and temporarily we will fix it as 2, and it will minimize. So the value would be less than equals to 2. Okay, so again, we've got a possibility that the value would be less than equals to 2, right? Now we update the value of beta here as 2. But when we go above and see the value of alpha, which was 4, it says that I already have 4. I was just looking for spaces or the score which was greater than 4. And you are giving me 2 here. That means it is not any way beneficial for me to go to your side and explore or waste my time, right? So what it does is that anyways, I'm giving you the space which will give me the maximum score or equal to score as 4. I just wanted that if I could maximize this or make it as 5 or 6, if I could get the score from traversing this space, I could have used you. But now since you're not giving me that, I will not go here. Okay, so what it does, it just says that, okay, I got 4 maximum, you are giving me 2, bro. No, I don't want that. So it will not go, and it will just prune this entire subtree of this big tree. So if I could just highlight this and tell you that this entire tree gets pruned, and here even this tree, this entire branch gets pruned, and this node gets pruned. So these searches are being reduced. We do not go and search these spaces. But in min-max, what we do is we go to the depth of the tree and explore everything, every node. But in alpha-beta pruning, we just eliminate what is not needed. And when we go down, it will not make any impact to our major decision. That means the final decision. That is why we are just pruning it. That means even if we eliminate these nodes, our final decision will not be affected. So just concluding that if we choose this path, we will get the maximum benefit rather than selecting the other path, which is just minimizing the score. Okay, and just it will lead me to losing, and this path will lead me to winning, right? So I will choose this path rather than this path, and alpha beta pruning helps me to quickly find this path rather than going and searching those spaces and nodes which will not give me any fruitful result. So the fundamental difference between the min-max and alpha-beta pruning is that we will not explore all the nodes in alpha-beta pruning. We will prune the nodes which are not required in our search spaces and will not affect our final decision. But in min-max, we will explore each and every node. Okay. So the complexity of min-max algorithm is naturally higher. It is order of levels to the exponential power of the depth of the tree. Whereas for alpha beta pruning, it could be just d by 2. So, and this is not in the worst case, but this is in the best or the average cases. In the worst case, it could just, happen that alpha beta pruning might have to search each and every space. So worst case is again worst, similar to min-max algorithm. So after having understood this, let us just sum up that alpha beta pruning searches the best path for the maximum player or the max player, that is alpha. It eliminates the parts of the tree and explores the less number of nodes. It reduces time, and also it returns the same number of moves like min-max algorithm, but it will prune away or eliminate the branches that will not affect our final decision. Okay, so now let's move on to our hands-on. So in our hands-on, we will be using alpha-beta pruning and min-max algorithm to implement a tic-tac-toe simple game. Okay, so before we go into running this big code and understanding what this code says, let us just run it and see the result and then understand the code. Okay, I'll just see the output and then I will show you how we got this code. So when we run this code, it simply asks you enter whether you want to play first or second. So I write here first. Okay, now it is again asking me enter any number between 1 to 9. So this is the board position. So I take the first position, and after that it gives me board, that is, this is my position X, and this is the computer which is playing with me, and it chooses this position, that is the 5th position. Now I will again choose a position between 1 and 9. So what happens if I choose 1? It says that it is an invalid move. Okay, because it has already been filled. So that is again a part of the coding which we have done here, right? Okay, so let me choose another position so that 0 doesn't win. That means I don't want computer to win and I want to win. So I'll choose this 9. Let's see. Okay, so computer just plays here at the 2nd position. So what do? Okay, I know that this can win when it moves at the 8th position. So I would simply choose this 8th one. Okay. And thankfully there's no trap right now. Now again there's a trap. See here, if I do not move here, that is the 3rd position, the computer would win and I would lose. And if I play here, I know that the computer will win. But if I play here, I know that next turn will be computer's turn. So naturally I will use 3. I will not let it win. So it could win, but it is my turn now. So I will simply use this position, that is the 4th one, and it says that it is a draw. Okay, it gives me the result, that is a draw. Had I win, it would have given me that you won. Had I lost, it would have given me you've lost. But since it is a draw and it is a very simple game, so that's why I could even visualize that if I move here, the computer will move next in which place. This is a very simple game, and that is why it is very easy to understand this thing. Now, important a few things that we have used in the code, which would be easy for you to understand. We have given the result, whether it is draw or it is win or it is losing by players. We have asked for the input from the user, that is whether you want to play first or second. Then we have again used the board positions, right? Then we have used the board, we have drawn this board. Again, we have drawn the computer chances. Then we have coded that if it is an invalid move, then it should what it should return, right? So let's see with various functions how have we really gone to make this tic-tac-toe code work. So we have imported random, and we have from this random library we have imported this packet choice, and from math we have imported this infinity, and we have given this board position. Okay, this is 3 by 3 matrix, that is what we have given. And then now we define game board, our board, and this is what our board looks like this is the simple specification of the board that we have seen here. This is the board that we are defining here in this code. Okay, so we visualize this board, we played in this board, that is what has been defined in this game board. Then we will clear this board, and as and when you play, the board will be cleared, right? Again, if you want to play, it will be cleared again. Now this is the function for the winner player, the player who wins. So I'm defining all the conditions, and these are the board positions like first, second, third, fourth, and all the positions till 9 positions. And these are the, I would say, the index, like the position in this array. This is 0 0, this is 0 1, this is 0 2, this is again 1 0, like this, right? Rows and columns. So I'm just defining with the index the rows and columns. And then it's an if and else condition, like if the player in condition, then you return true, otherwise return false, right? So now another function is game 1. So if you won the game, what it will return. Another function will be the print result. So like we saw the print result that it was a draw, so it has given me a draw. If I would have won, it would have given me that X has won, and if the another player, that is the computer, would have won, it would have given as 0 has won, right? Okay, then I will just define the blanks in the board. I will also define the board full. So if the board is full, what will happen? And I will set the move. So these are the various things that I'm setting that we have already seen. Okay, that's why we are going fast. So we are setting the move here for the board, for the players, for X and Y. So this would be used again and again. So these the board full, set move, player move, these functions will be called again later on. And this is the player move. So now when the player moves in the board, and if the position is true, that means if you're moving in any of these positions like 1 to 9, then what will happen? So it will try. So I'm using this while and try loop here, try and accept if you have to catch any exception here. And that's what we did, we just entered something which was not valid, and it gave me invalid move, try again, because the board was full. So we had taken care of all the exceptions that could possibly occur in this code. So this is the block for that. So using all the Python necessary control loops and the exception programming here. And then we will go on to setting the score. That is, we will define a get score function here. So this function will set the player win, that is the board 1, it will return 10, else if it will return -10. So this board works, and then again we will be using this function later on. And then we will define our alpha, beta, and board, the depth, and also the player here in the AV min-max function. So we give the row, we give the column, and now we start with the depth, and in alpha, beta pruning we have to give the depth, right? So we say that if it is 0 and if it is game 1 board, then what you do, you return this row, column, and the score. Else, you just iterate this. And in else, again, we've got for loop, if, and within this, we've got if else. And this is a big loop because we have to define the alpha and beta here. That's what we did. And now this is calculating the score at each node. And here, when the score 2, now suppose if player 1 is moving here and score 2 is greater than alpha, then these things would be met. Else, if it is less than beta, then the score would be fixed beta as like the score 2, and then the rows and the column would again be updated, right? So this is how we are updating alpha and beta at every move, and this is what this loop is doing. So once we get the alpha and beta value, we can decide the next move. So this is the coding for that. And then again, we give that if alpha is greater than beta, then break. And this is the main condition that has to be fulfilled. And then if player equals to 1, it will return alpha, else it will return beta. That means the player 1, that means maximizing. Alpha is maximizing and beta is for minimizing the score. Now we are defining the two competitors, that is the players. So 0 and cross. So the 0 competitor that is in the board. So now we will define two functions, that is for the players, that is 0 and X competitors. So for 0, we will define this function, and these are the moves that 0 competitor or the player would take. and this x would be, this function would run when the x player will move or will decide any choice in the board. So this is what we have seen while we were running. And then if not all these things would be fulfilled, then again there's an else loop wherein it will return, or the result would be the same function that we called here, this function would run, right? So that's quite a big code because we have to decide everything. Now what we do is we make a move here. So again, defining a function with board, player, and more. And this is again in an if and else condition, nested if and else. Then we will define the result wherein we got all the results, again trying it with while and try an exception block. So again we will try, and the sequence would be again, so it is taking an input from the user that enter whether you want to play first or second. That is what it has asked us. And then it will say that please pick a number between 1 to 9, and that is what we've entered here. And the sequence will break if there's any exception or value error. Then we will clear the board. Again, if you want to play this, we can clear the board again. And if there is a full board, that is here, it will just show me the result. That is what we have printed here, the result. And this tic-tac-toe with alpha beta pruning, we just printed this, and this is a separator line just for the aesthetics part of it, right? So this was the entire coding of this small tic-tac-toe that we have just played with the computer, and we made sure that this doesn't win at any cost and there's a draw. So neither I won nor the computer, right? So this was very simple because the state spaces I could visualize, the computer could visualize with the help of updating alpha and beta. So with this, I am making the computer intelligent enough to understand the various state spaces in this game and make it move accordingly. So this is what alpha beta pruning is all about, and this just played so fast that it was really fun playing with this computer. And when I raised the difficulty of this game, it would even become more and more interesting. Suppose I just have a 3 by 3 matrix here. If I could just increase these blocks to 16 by 16, imagine the difficulty. Now imagine if I just increase the complexity of this game. This is just a 3 by 3 matrix. And if I just make it to 9 by 9 or 16 by 16, imagine the moves, the spaces, and the searches that the algorithm would have to make. And since alpha beta pruning we are using, it would minimize these, nodes, traversing these nodes or searching these nodes. And we would really enjoy playing with computer because it would be fast, and with no time it will give us results. So this is how you can really, create your own tic-tac-toe using alpha beta pruning and play with computer, raise difficulties. You can just increase the size of the board and define various other conditions in different functions, right? So now after our hands-on, let us understand the significance of alpha beta pruning. So this is an algorithm which helps to develop games which enhances the practical skill of players. Also, it sharpens the brain. It is very good exercise because when you play the games, board games like chess, checkers, it just helps you to sharpen your brain. And it is also used for educational stimulation and psychological roles. And these helps really in strategic decision making. So when you're playing chess, you're actually strategizing various moves the opponent could take, your wins, your loses, and you are just having all these calculations in your head. So it gives you a lot of scope to improve the brain exercise, make good strategic decisions, and improve your practical skills. So now let's move on to the advantages and disadvantages of alpha beta pruning. So let's cover the advantages. So in advantages is that it helps in reducing the number of nodes, as we have seen in the working. It reduces the time and space complexity, and this again links to limiting the number of nodes and reducing the time and space complexity involved in alpha beta pruning. It improves the search, and it is really fast algorithm when we compare it with minimax algorithm. And also it is an advanced or an optimization algorithm for minimax and an advanced version of minimax algorithm. So this was the advantages of alpha beta pruning. Now let us move on to the disadvantages of alpha beta pruning. So the first one is that it does not solve all the problems which are associated with minimax algorithm. That means that sometimes it will explore all the nodes, and that is the worst case scenario. Another thing is that it requires the depth limit. So you have to specify the depth limit. And this is really not feasible for most of the cases where we cannot determine the depth limit. For tic-tac-toe, it was possible because the game was small. Imagine if it's chess, you cannot determine the depth of the tree, right? because the game become complex. There are many various possibilities of game spaces and moves which cannot be just calculated and told to the algorithm. So it becomes a little difficult. Alpha beta is designed to select the best move, but it also calculates the value of all the legal moves. So there's no improvement in certain cases when we apply alpha beta pruning. So there are certain advantages and disadvantages that we have discussed for this algorithm. And I hope you would have learned a lot of things about alpha beta pruning and how it really helps in designing games in artificial intelligence, especially the board games. And that's it from my side. Thank you.
I hope you have enjoyed listening to this video. Please be kind enough to like it, and you can comment any of your doubts and queries, and we will reply them at the earliest. Do look out for more videos in our playlist and subscribe to Edureka channel to learn more. Happy learning!